All right, physics cool dudes. This is the second part of engineering physics, where we're going to be doing the introduction to torque and rotational inertia. Last class we talked about rotational motion and the kinematics of rotational motion, and I just wanted to start this lesson off on doing a review problem to see that we've covered everything that we needed to cover last class. All right, so this question is a classic question about bicycles, where we're looking at the rotation of the tires on the bicycle. Okay, the question is, a bicycle slows down uniformly from initial linear velocity of 8.4 meters per second to rest over a distance of 150 meters. Each wheel of the bike has an overall diameter of 68 centimeters. So we're going to use that information to solve the rest of these problems. The first problem is to determine the initial angular velocity of the wheels. How do we do that? We got to remember some formulas, some kinematics formulas. Remember, all the linear kinematics formulas can be converted into angular kinematics formulas by dividing by r. So my angular velocity is going to be equal to my linear velocity divided by the radius of that tire. And the radius of that tire is going to be half of 68, which is 34 centimeters. So the linear velocity is 8.4 meters per second divided by 0.34 meters is going to give us 24.7 radians per second, I believe. Okay, so that is our, oops, what happened there? That's our angular velocity. Okay, calculate the total number of revolutions that each wheel rotates before coming to rest. So how are we going to do that? How are we going to figure out how many times that wheel rotates? Well, first of all, if I take a look at, I need to figure out the total distance is 115 meters. So the bike is going to travel a distance of 115 meters. All right, and this is, I don't have to do much in terms of using my angular velocity or things like that. I could if I wanted to, or I can use some logic. And let's cheat. Let's use some logic here that the circumference of the tire is equal to 2 pi r. So one rotation of the tire is going to give me that circumference. So 2 pi times 0.34 meters is going to give me the distance traveled by the tire. All right, so then if I take 115 meters divided by 2 pi times 0.34 meters, which is the circumference of one revolution, 115 divided by the circumference of one revolution will tell me the total number of revolutions, which is 53.8 revolutions. Okay, that's pretty simple. So I cheated. Now there's other ways I could have done that. Okay, I could have used my angular velocity, my acceleration formula. I could have used the Suvat formula to calculate theta, the total angle of my angular displacement. And remember, 2 pi is equal to one rotation. So if I would have calculated my total angle and divided by 2 pi, I can also get those revolutions. So we kind of cheated to avoid doing the hard stuff, which is calculating my angular displacement. All right. The next question is to calculate the angular acceleration of the wheel. Okay, so let's remember some of these formulas. All right, so acceleration or angular acceleration is going to be equal to my final angular velocity minus my initial angular velocity divided by time. That would be 1. Do I have time? No, I don't have time, so I can't use that. So I got to go back to some of these formulas. All right, so I don't have time. Because I don't have time, let's figure out what other formulas I have. All right, so for me, because I don't think about these kinematics formulas in the form of angle, I like to go back to all my Suvat equations. I'll just write them down first. So S is equal to UT plus 1/2 AT squared. And if I divided all those variables by R, I can get the angular components of it. Okay, what else do we have? V squared is equal to U squared plus 2AS. Okay, both of those formulas have relationships in them that we can use. Okay, and then A is equal to V minus U divided by T. So I can't use those, right? So if I wanted to calculate the angular acceleration, I need to look what I have. I have my displacement. I have S, okay? I have my initial velocity or angular velocity. I don't have time, so I can't use that anywhere in here. But I do have S. All right, so what I could do is I could use the angular equivalent of these formulas. I'm going to select this formula over here. What would the angular equivalent of that formula look like? Okay, well, the angular equivalent of that formula is going to look like this. Okay, that's the angular equivalent of that formula. All right, so if I wanted to solve for the acceleration, this would be my final angular velocity minus my initial angular velocity squared divided by 2 times theta is going to be equal to my acceleration. All right, so how do I find out theta? Well, I can use this that I have up here. 53.8 revolutions is how many revolutions I made. If I multiplied that by 2 pi, that'll tell me my angular displacement. All right, so if I plug these numbers in, if I plug 24.7 radians and I squared that here, okay, and then this is going to be 0 radians per second squared, right? And then 2 times 53.8 revolutions times 2 pi, if I put all that together and substituted it in, which you guys can do right now, and pause the video and do the calculation, you'll be able to calculate not my linear acceleration, but my angular acceleration. That's what it should look like here. Okay, so pause the video and calculate that. All right, now if you calculated that, your angular acceleration should be equal to negative 0.902 radians per second squared. All right, now with all that information, we can calculate the total time taken for the bike to come to a stop. And how we're going to do that is using this last formula that I drew out over here. That's the linear one. I can convert it into the angular formula. So converting that into the angular formula, my angular acceleration is equal to my final angular velocity minus my initial angular velocity divided by time. If I rearrange that equation, time is going to be equal to my final angular velocity minus my initial angular velocity divided by my angular acceleration. So time is going to be equal to 0 minus 24.7 radians per second divided by negative 0.902 radians per second squared. And time is going to be equal to 27.4 seconds. That's interesting, kind of strange. All right, so with all that together, here's a good example of a problem where we are covering all the aspects that we did last class. There's many different variations of these problems, but we have to be comfortable with units such as angular velocity, okay, revolutions, angular acceleration, the symbol for angular acceleration, converting all these linear kinematics equations into angular kinematics equations, okay, and then playing around with angular velocity calculations to calculate times of rotations and things like that, okay? So then now we're ready to talk about the forces that cause objects to rotate, okay? So it's not really the force, it's what we're talking about is a unit called torque, okay? And we hear torque a lot when we think about cars, when we look at how much torque does that engine have. Or another area that we talk about torque is what you see here in this diagram, a torque wrench. We apply torque to a nut or some type of bolt, okay? And sometimes if you put too much torque on a bolt, you can seize it or you can break it, right? So if we're dealing with delicate systems, okay, like for example, engines in a car, all the bolts in your car have a suggested amount of torque to put onto it. If you don't put enough, the engine is going to vibrate. If you put too much, you might seize that part and it'll be impossible for you to take it off. It might put too much stress on the system. So mechanical engineers often work with torque, okay? Now this is a special type of tool called a torque wrench. It has a sensor in it and it has a little dial over here that will measure the amount of torque being applied. So as you're tightening it, a little number is going to appear here, and it's going to tell you exactly how much torque you're applying. So you would stop pushing when that torque reaches a certain value, and then you know that you've tightened all the bolts to that. A very useful tool to have, okay? So torque causes objects to rotate. And what it really is, torque is not a force. Torque is the combination of, it's the product of force being applied by a distance away from the axis of rotation. So if I take the force that I'm applying perpendicularly to the axis of rotation over here, this distance would be called the moment, okay? That moment. So from the center of rotation, that axis of rotation, out to where I'm applying a force, that distance is called a moment. So force times that distance, and it's the perpendicular force times that distance, would give me torque. Okay, we can see that in this formula here. So torque is equal to the length of the arm, or that moment, the moment arm, okay, that length, times the perpendicular force would give me torque. Okay, in this diagram that you see up here, I'm sure if you ever used a wrench, you would realize that if you try to push the wrench close to where the nut is, it's really hard to move something. But if you move further away on the wrench and push there, it becomes easier to turn that bolt, okay? And that's because the value of torque that you're applying here, or the moment that you're applying here, is going to be greater than the moment you apply here. So the torque here would be much greater than the torque over there. Torque is going to be directly proportional to my angular acceleration, making that much easier to turn that bolt. You'll see tricks sometimes when you're going to, later in life, when your tire pops and you're stuck on the side of the road and you take a wrench out to take the tire off, to unloosen the bolts, you're not able to do it. And then a mechanic shows up, he takes another wrench and it attaches it to here, makes it longer, and then he can loosen it very simply with just his finger. All right, because he increases the torque being applied, making it easier to rotate the bolt. Okay, and this diagram down here is showing you that in order to calculate torque, the force that I'm applying has to be perpendicular to that moment arm. All right, so this angle over here is showing that it's not exactly perpendicular. So sine of that angle will show me the perpendicular component that I'm applying to that moment arm in order to create torque. So remember, torque is the perpendicular. The force and the moment arm are perpendicular. All right, and that's how I can calculate torque. All right, and the last thing we're going to talk about is just defining what torque is, moment of inertia, or the relationship between torque, moment of inertia, which we're going to figure out over here, and angular acceleration. Okay, so in these examples I said, the angular acceleration of that bolt is directly proportional to the amount of torque that I'm applying. And that's what it says over here. The angular acceleration is directly proportional to the sum of the torque. Okay, well, what does that mean? It means if actually I was applying a force here and a force here at the same time, I would add the torque that I'm putting in here, force times that distance, plus force times that distance would be the total torque, and the total torque would be proportional to my angular acceleration, okay? Well, it so happens that because force and acceleration and torque and angular acceleration are related, they all follow Newton's second law relationships, okay? Torque is there's a Newton's second law of rotation, and it relates to torque, okay? So how would I convert Newton's second law of equation for point masses into equation for rotation of a point mass? That's this equation over here. This is torque. This is mass, that's the radius or the moment squared times my angular acceleration. So how did he derive that? How did he convert that to that? So what this equation is saying is if I took this point, that's my point mass right over here, and I applied a perpendicular force, I'm going to cause it to undergo angular acceleration. All right? So they're both for point masses. Both equations here are for point masses. Okay, so how would I go about converting that into that? All right, well, I'll show you pretty quickly. All right, so if I applied a perpendicular force, okay, times the radius, force times radius is going to be my torque. That's how we get that. So whatever I do on the left-hand side, of this equation, I have to do on the right-hand side of that equation. So if I'm going to multiply F times R to be able to get torque, I have to do the same. So the first step would be to multiply both sides of that equation by R, and I'll be getting MRA. Okay, we're not done yet. Now the next step is how do I convert A into angular acceleration, or vice versa? How do I convert angular acceleration into A? Okay, well, if I'm going to substitute angular acceleration into here, angular acceleration can be converted into a by multiplying the angular acceleration times the radius. So this goes down a little further. F times r, which is my torque, is equal to m times r times alpha, okay? And then if you can take a look, that's exactly how that equation came. M times r squared, times alpha is equal to torque. So what do these terms mean? Okay, well, this term in here is defined as the inertial mass. Okay, that'd be the inertial mass of a point. Okay, the point that that point mass here, the inertial mass of that point mass that I'm applying right over here, the inertial mass at that point. Okay, because that's analogous to m in that formula. A, or alpha, my angular acceleration, is analogous to my linear acceleration, and force, okay, force is analogous to torque in that second law relationship. So the inertial mass, mr squared, which in your data booklets has a symbol of I, okay, you would see that there's another formula that we create that looks like this, okay? Torque is equal to I alpha. Okay, now why don't they just say mr squared alpha? Well, the inertial mass is not the same. The inertial mass of an object that we're pushing is not a point mass, okay? When I'm looking at an object, let's say I'm looking at this object over here. Yeah, I'm looking at, why isn't that showing up? I'm looking at this object over here. If I'm pushing it over here, I'm not only pushing that point, okay, I'm pushing all these little other point masses and making them move. Okay, so the inertial mass would be a sum of the torque at all these points when I'm applying. It's an average, all right? And that average is going to come out based on the sum of all the inertial masses. It's going to be a fraction of mr squared, because I have to average. I'm not actually applying a force over there, but I have to calculate the magnitude of force that I'm applying from that. My force is being applied here, and I'm moving an object over here. There's a component of that force being applied. So if I sum all the inertial masses of points along that arm when I'm pushing it, I will get the rotational inertia. Okay, and if you take a look at these objects, depending on the shape of the object, the mass distribution, and the symmetry of it, you'll see that they have different equations for I. Okay, so if I was rotating a hoop about the central axis, I looks exactly the same as we put over here, mr squared. Okay, because I'm moving points of mass that are acting only on that radius. So it's as if I'm moving just that point mass at the radius. There's nothing inside, so then it behaves like a point mass. I equals mr squared. But once I start to put weight on the inside, more particles on the inside, you don't see mr squared anymore. You see some more complicated fractions. 1/2 mri squared, the inner diameter, and the outer diameter finds the average of all those point masses. Okay, and then you can see all these different types of objects that I'm rotating. All right, depends on how I'm rotating them, I get a different inertial mass formula. Okay, so what I'd have to do if I'm solving a problem, it's asking me, this looks similar to that rotational motion apparatus that we have in the lab, where the central axis is rotating here. Well, the moment of inertia of that big arm is equal to 1/12 ml squared. Okay, so if anyone did an IA on that, they would have to understand that the inertial mass of that arm is going to be 1/2 ml squared. It'd be an interesting IA if we put the masses at different places and we took a look at the torque that we'd have to apply and see how the angular acceleration would change by where we put the masses on the object. I think I'll get a kid from grade 11 to do that this year. Or you can change the objects that you put on that rotational motion apparatus and get some different ideas. Okay, so to sum this all up, if they gave you a question with different objects, you would have to take the inertial mass formula. They'd probably give that to you, or I'd give that to you. And then you'd plug that inertial mass formula in for I. All right, and then torque is calculated by the force the perpendicular force that you're applying times the radius at which you're applying it. Okay, so torque divided by my inertial mass would give me my angular acceleration. So in the next video that I make, I'll be doing some sample calculations with this torque formula. All right, thank you.